This is the video to accompany the Chapter 8 notes, Part 2. This video is going to be a little bit different than the ones we looked at before where we had the PowerPoint slides. In these videos, we're going to look directly at the notes and I'm going to highlight some different pieces. Part of this is here in a couple pages, we're going to get to some parts where we're going to do some calculations and we're going to have a lot to write. So when I get to these spots, I wanted to be able to write everything down so you can see exactly how I work through the problems and what your answers should look like. So in section 8.2, we're going to look at constructing a confidence interval to estimate a population proportion. In other words, what we're going to do is we're going to use our statistic p hat to estimate the parameter p. So we're going to use p hat to estimate p. That's our goal here. And so if you'll recall from our previous sections, we saw that a confidence interval can be given by the statistic plus or minus the margin of error. What we didn't talk about so far is where the margin of error comes from. How do we calculate it? And so we have here that the margin of error reflects the precision of the sample statistic as a point estimate for the parameter. The margin of error is constructed by taking into account the standard error and the percentage of intervals that would cover the parameter based on the behavior of the sampling distribution. This gives us to how we're going to calculate the margin of error. Our margin of error, which again is this piece up here, is equal to the critical value times the standard error. And so our critical value and our standard error are going to depend on what type of statistic we're working with. So in this section, again, we're going to work with the statistic p hat to estimate the parameter p. The critical value portion of this formula is the piece that's going to account for the percentage of intervals that would cover the parameter based on the behavior of the sampling distribution. The standard error reflects the variability of the statistic. You already learned about standard error in the Chapter 7 notes. So this next piece is just talking about what happens to the margin of error as we do two different things. Well, as you saw previously in Chapter 7, when we change our sample size, that changes our standard error. So notice here the first question is, what happens to the margin of error when we change the sample size? In other words, this is asking is what happens when the standard error changes. And so notice the larger the sample size, the more precise the statistic is as a point estimate. Larger sample sizes will produce smaller margins of error. This is because you learned in Chapter 7 that larger sample sizes produce smaller standard errors. So when we have a smaller margin of error, this will produce a more narrow confidence interval. On the other hand, smaller sample sizes, the less precise the statistic will be as a point estimate. Smaller sample sizes will produce larger margins of error. And again, this is directly related to what happens to the standard error when we change the sample size or have small samples, and you saw this in Chapter 7. So what happens to the margin of error when we change the level of confidence? This is the same as what is asking what happens when we change the critical value. Recall that the confidence interval is the proportion of all samples whose intervals contain the parameter. To change the proportion of all samples whose intervals contain the parameter, we need to widen or shorten the confidence intervals. The higher the confidence level, the larger the margin of error. Since the margin of error is larger, this will produce a wider confidence interval. The lower the confidence level, the smaller the margin of error. Since the margin of error is smaller, this will produce a more narrow confidence interval. So notice to find the margin of error, we need two different things. We need to talk about the critical value and the standard error. We already talked about the standard error in Chapter 7, so now we're going to spend some time talking about how we can find the critical value. So when working with a single proportion, and notice this is dependent on working with that single proportion, the critical value will come from a standard normal distribution. And so this is one of the reasons it was so important we talk about standard normal distributions earlier in the course. And so as a reminder, a standard normal curve has mean 0 and standard deviation 1. So we're going to look at how to find critical values from a standard normal distribution. The critical value accounts for the percentage of intervals that would cover the parameter based on the behavior of the sampling distribution. When working with a single proportion, or even difference between proportions, which we'll see in Chapter 10, we know that the sampling distribution is normal if the sample size requirements are met. When the critical value originates from a standard normal distribution, we denote it by Z star. And we can find Z star for a p% confidence interval by doing the following. We start by drawing a standard normal curve. We shade in the middle p% of the curve, and we find the positive endpoint. That positive endpoint will be the value of Z star. So previously, you saw how to do problems like this, not necessarily in terms of Z star, but shading the area under a normal curve using both stat key and your standard normal table. So here we'll look at an example of what this would look like in stat key. For example, if we wanted to find the critical value for a 99% confidence interval using a standard normal curve, we could do the following. First, we would draw a standard normal curve. So you could go to stat key and draw that standard normal curve, remembering that the standard normal curve has mean 0 and standard deviation 1. Alternatively, we could just draw this picture on our paper. Next, shade in the middle 99% of the curve. Now remember, stat key actually shades the tails, so we can think of this as being shaded in white, but we have the middle 99% marked. So we have 99% in the middle, and again, you could have just drawn this on paper. And then we need to find the positive endpoint. So the positive endpoint is the value down here at the bottom. Stat key automatically gives this to you, or you could also use your standard normal table to find this value. Notice that the area to the left of this point is 0.99 plus 0.005. So this Z star has area 0.99 plus 0.005, which is equal to 0.995 area to the left. And you saw previously how to use your standard normal curve to find endpoints like this. And so notice here in your notes I have two separate videos. You can watch this video to see how to use stat key to find different Z stars. So very similar to the printouts that you see here. And then you could use this video down here at the bottom, and I show you how to use the standard normal table to find Z star. And again, you're basically using the skills that you developed previously when working with different normal curves to find these values. Listed here on the top of page 13 are some of the more common values for Z star. Notice here's the value for the 99% confidence interval that we just found earlier. Next, what we're going to do is we're going to go through the basic steps of calculating a confidence interval. Then we're going to look at how we would calculate a confidence interval for a single proportion, and then we're going to do several examples. So up here at the top, we have the basic steps for calculating a confidence interval. These steps are going to work no matter if we're working with means or proportions, so we're going to look at everything generically first. So you want to start by determining which type of parameter you're interested in learning about. Then identify each of the parts needed to compute a confidence interval. To use the formula for a confidence interval, we first need to confirm that the sample size requirements for the central limit theorem are satisfied and that the sample is random. Next, we need to identify two things to compute the confidence interval: the statistic, also known as the point estimate, and the margin of error, where the margin of error is equal to the critical value times the standard error. Combining these, we get our formula for our confidence interval, which is the statistic plus or minus the margin of error. Lastly, we need to interpret the confidence interval. The interpretation of a confidence interval should always include three things: the level of confidence, reference to the parameter and context, and the calculated interval. So next, we're going to look at the steps for calculating a confidence interval for the population proportion. You'll notice that for each scenario we are describing the basic steps of calculating the confidence interval. And so this is referencing when we move on to means as well. But for right now, we're going to look at each of the steps above, but now we're going to write it in terms of calculating that confidence interval for a single proportion. So when we work with a single proportion, the parameter we are interested in is P. So to use the formula for a confidence interval, we first need to confirm the sample size requirement for the central limit theorem is satisfied and that we have a random sample. For a single proportion, we need to check the following sample size requirements. We need that our sample size times our statistic is greater than or equal to 15. And we need that our sample size times 1 minus our statistic is bigger than or equal to 15. This is the same as having a count of at least 15 in each of the categories. From here, we need to identify two things, our statistic or our point estimate. When the parameter we're interested in is P, the statistic is P hat. To get our margin of error, we'll find our critical value using the standard normal table, and then here is our formula for our standard error. Next, what we're going to do is look at several examples where we work through each of these steps to calculate that confidence interval for a single proportion. Finishing out the steps on the previous page, notice here we've got our statistic plus or minus our critical value times our standard error. So this whole piece on the left here, this is our margin of error. And then don't forget, we are going to need to interpret that confidence interval. So now let's look at an example. In this example, we've typed, the entire solution is typed out for you, so you can see what a solution looks like. I'll talk through the solution, and then we're going to work several of these problems together. So starting with the example, it says, suppose a researcher is interested in the percentage of Kentucky coal miners who have developed lung disease during the course of their career and would like to calculate a 90% confidence interval. The researcher takes a simple random sample of 250 coal miners from Kentucky and finds that 175 have had lung disease during the course of their careers. Alright, so first of all, notice here we are going to construct a 90% confidence interval, and we are working with proportions here because our variable of interest is whether or not the coal miners developed lung disease. So here this is a categorical variable. The answer will be yes or no. They spoke to 250 coal miners and they found that 175 of them had the lung disease. So the first thing we're going to do is our sample size check. We could also, instead of sample size check, we could also write this as assumptions. These are the things that we need to hold true in order for the methods we look at to work. So first of all, notice that there are 75 coal miners with lung disease. And since we talked to 250 coal miners total, that means there's 250 minus 175, which equals 75 without. So in other words, this without number comes from the 250 minus 175. Since the counts in both groups are greater than 15, and notice they tell us we have a simple random sample of coal miners, the requirements are satisfied. So now we're going to go through and calculate our confidence interval. First thing we need to do is calculate our statistic, which is also known as the point estimate. There were 250 coal miners total, and of them, 175 developed the disease. So this gives me my statistic of 175 divided by 250 is equal to 0.70 or 70%. Next, we need to get our critical value for a 90% confidence interval. The quickest way to do this is to look at the top of the previous page, page 13. So notice on the top of page 13, we have that the critical value, or the Z star for a 90% confidence interval, is equal to 1.645. But for illustration, let's talk through how we could find this value using our standard normal table. So using our standard normal table, what we would do is we would first start by drawing a standard normal curve. Recall that the standard normal curve is centered at 0. Next, we would shade the middle 90% of the curve. Z star will be the positive endpoint. Notice that if we have 90% in the center, that means I'm going to have 5% down here and 5% in this tail. So this value right here has 95% of the curve to the left. Using that information, we could look that value up on our standard normal curve and find that we have an endpoint of 1.645. Next, to get our margin of error, we need to calculate our standard error. So I'm going to start by first writing down the formula. And you'll notice for each of these problems, that's where I start, and I highly recommend you do that on your page as well. Next, I'm going to fill in all of the values. So notice that our p hat here was equal to 0.7. So for each of the p hats in the formula, I filled in a 0.7. N is our total sample size. So our total sample size was the 250 coal miners. So we have a sample size of 250 here. Sorry, I should say the sample size is 250. The sample was the 250 coal miners. Placing this in your calculator, you'll get a standard error equal to 0.0290. Now that we have our statistic, our critical value, and our standard error, we can combine these three pieces to calculate our confidence interval. So looking down below, notice here, the p hat is our statistic, the z star is the critical value, and then the rest of it is the standard error. We found all three of these up top, so plugging in the values. For the statistic, we found 0.7, so we plug in 0.7. For the critical value, we found 1.645, so we plug in 1.645. And for the standard error, we found 0.0290, so here we plug in 0.0290. Multiplying these two together gives 0.0477. Taking 0.7 minus this value gives us this endpoint, and taking 0.7 plus this value gives us this endpoint. So notice this interval, what it's saying is any number between these two numbers is a reasonable value for our parameter. Also, be careful when writing out your intervals. You always want to go from smallest number to largest number. And then finally, we're going to interpret our confidence interval in context. So remember that interpretation always needs to include three things. The first is our level of confidence. So we say we are 90% confident. Next, we reference the parameter in context. The proportion of Kentucky coal miners who have developed lung disease during the course of their careers. And then finally, we give the interval that we calculated. So here is a typed out example. Now what we're going to do is we're going to go through another example together where we work through each and every one of the steps. This example reads, many people consider themselves green. They support, in theory, environmental issues. But how do they act in practice? For instance, Americans' per capita use of energy is roughly double that of Western Europeans. If you live in North America, would you be willing to pay the same price for gas that Europeans do? This is usually about $8 more per gallon. If the government proposed a significant price hike as an incentive for conservation and driving more fuel-efficient cars to reduce air pollution and its impact on global warming. This should say in 2010. So in 2010, the GSS asked subjects whether they would be willing to pay much higher prices to protect the environment. Of the 1,361 respondents, 637 individuals indicated their willingness to do so. We're going to construct and interpret a 95% confidence interval for the population proportion of adult Americans willing to pay higher prices to protect the environment. So, the first thing we need to do is check our assumptions. There are two assumptions that we need to check. The first one is that we need the random sample. Notice, in our prompt, we're not given information about whether or not the sample was random. Since we don't know if the sample was random or not, we will proceed with caution, realizing that the conclusions we come up with may or may not be valid, and we really need to confirm whether or not this was a random sample. 2, we're going to do our sample size check. So first of all, notice there are 1,361 respondents minus 637, which is equal to 724 people who said no, and 637 who said yes. Both values are greater than 15. Since both values are greater than 15, the requirements are met. Next, we're going to find the different pieces we need to calculate our confidence interval. The first thing we need is our point estimate. And remember, that's the same as our statistic. Since we're working with a single proportion, our statistic is p hat. And since we're interested in the proportion of people that are willing to pay, we had 637 say yes out of the total of 1,361. Placing these values in our calculator, we'll find that p hat is equal to 0.4680. You'll want to take most of these calculations out to 4 decimal places, otherwise you're likely to end up with round-off error. Next, we need to find our critical value. And here, we're working with 95% confidence. So we could go to one of our charts, because this is one of our common values. So again, we're going to go to the top of page 13 of our notes. And notice for a 95% confidence interval, our critical value is 1.96. Next, we need to find our standard error. So for our standard error, I'm just going to write out the formula. The formula that we have is p hat times 1 minus p hat divided by n, where n is our sample size. Well, we already have p hat right here, and our sample size is the 1,361 people. So plugging in those values, Placing in our calculator, we'll find this value is equal to 0.0135. Now that we have all three of these pieces, we can calculate our confidence interval. I'm going to start by writing down the formula. And now that we've already calculated all three of these pieces, I'm going to go ahead and fill them in. So p hat was our point estimate or our statistic. Z star was our critical value that we found up here. And then this piece right here is our standard error, which we calculated right here. Now I'm going to multiply the 1.96 times the standard error. And then finally, to find the confidence interval, I'm going to take this value minus this value and this value plus this value to get my interval. The last thing we need to do is interpret our confidence interval. So I'm running out of room here, so I'm actually going to write my interpretation right below part B. So we're going to kind of continue this on to right here. So the last thing I need is my interpretation. Now remember, for our interpretation, we need three different things. We're going to start out with our level of confidence. So we are 95% confident. Next, I'm going to reference my parameter in context. So notice here, and sorry I skipped ahead a little bit, this piece right here, this is our level of confidence. This piece from here all the way to here is our parameter in context. And then the last piece we always need is to give our actual interval, which is the last piece right there. Notice our last question here is there evidence that fewer than half of U.S. population is willing to pay higher prices? So notice, our interval gives us a range of reasonable values for the parameter. This entire interval lies below 0.5. So we do have evidence. Yes, the entire interval is below 0.50 or half. Now we do have to be somewhat cautious here because remember, we didn't have that random sample assumption. Since we don't have the random sample assumption, we need to be careful about this conclusion. But if we went back and were able to talk to the researchers or the people who gave the survey and confirm that that was a random sample, then we would be able to make this conclusion. Let's look at another example. This one says, according to the Centers for Disease Control and Prevention, the single best way to protect against the flu is to be vaccinated. Traditionally, flu vaccines are manufactured using viruses grown in chicken eggs. A new method allows growing viruses in cell cultures instead. To test the effectiveness of such vaccines, in a recent clinical trial, N equals 3,900 randomly selected healthy subjects aged 18 to 49 received a cell-derived influenza vaccine by injection. During the follow-up period, approximately 28 weeks, each subject was assessed whether he or she developed influenza, which happened for 26 of the 3,900 subjects. We're going to construct and interpret a 95 and a 99% confidence interval, and then we're going to compare them. All right, so we're going to start out with the 95% confidence interval first. And so, as always, the very first thing we're going to do is check our assumptions. First thing we're going to do is check for our random sample. And yes, this was given in problem. Notice here we've got randomly selected healthy subjects. 2, we need to check our sample size. We had 26 people who developed. It says, right, that who developed the flu. And we had 3,900 minus the 26, which is equal to 3,874 who did not. Both are greater than 15. So we have met the requirements. All right, so now we're going to go through and calculate our confidence interval. We're going to start out with our point estimate. Remember again that your point estimate is the same thing as the statistic. So in this case, we have that p hat is equal to 26 because we had 26 people who developed the flu divided by the total number of people, which is 3,900. Placing this in your calculator gives 0.0067. Next, we need our critical value. Again, to find the critical value, you could either use those common critical values on page 13, since this is one of our common critical values, or you could compare it to the standard normal distribution. So here again, we've got our z star, or critical value, is equal to 1.96, since we do have that 95% confidence. And then finally, we need our standard error. And so writing down our formula, remember the formula is p hat, 1 minus p hat, divided by n. We take the square root of that. So now we're going to plug in our values. That gives us 0.0013. And then next we can calculate our confidence interval. Recall the formula for the confidence interval is p hat plus or minus z star times the square root of p hat 1 minus p hat divided by n. Now notice here I'm not putting an equal sign, I'm putting an arrow. And so what I'm going to do next is fill in all the pieces for that formula. And then if you take your point estimate, one thing to note here is do note that this full piece together, this is the margin of error. Again, this piece right here is the point estimate. So if we take this value, we do our multiplication here and subtract, then take this value, do our multiplication and add, the interval that we'll end up with is 0.0042 to 0.0092. So that gives us our confidence interval. And then for our interpretation, we are 95% confident. So there's our level of confidence that the proportion of people, and notice here we should probably we should be more specific here, because notice they only tested healthy subjects age 18 to 49. So we'll say healthy 18 to 49 who develop the flu, that's just FLU, on the vaccine is between 0.0042 and 0.0092. Alright, so that's the 95% confidence interval. Next, let's construct the 99% confidence interval. Now to save space here, I'm not going to go through and check the assumptions, because the assumptions for the 95% confidence interval and the 99 are exactly the same. Really, the only thing that changes when we go to compute the 99% confidence interval is our critical value. So only the critical value, oops, wipe that out. And so our new critical value, if we're working with the 99% confidence interval, again, if we go and look at that table of common values, which is on page 13, notice that Z star for a 99% is 2.576. So here, Z star is equal to 2.576. So take a moment and pause the video and see if you can recalculate this interval, where the only thing that changes is the 1.96 changes to 2.56. When you come back, I'll tell you what interval you should get, and then we'll compare our 99% to our 95% confidence interval. Alright, when I calculated the 99% confidence interval, what I did was I took my point estimate of 0.0067, sorry about that, and I took plus or minus 2.576, multiplied that by 0.0013, the interval that I found was 0.0034 to 0.0100. So let's compare our 99% confidence interval to our 95% confidence interval. In other words, which one is wider? And the answer here is you should notice that this interval is wider than this interval. What this tells us is that more confidence equals wider intervals. And we actually already discussed this fact. So if you turn back to page 11, recall here what happens to the margin of error when we change the level of confidence. Well, recall that the margin of error controls how wide the confidence interval is. So here, for this problem, when we increase our level of confidence, notice if we look at the actual formulas for our confidence interval, the point estimate didn't change. It's the margin of error that changes from piece to piece. And this margin of error is larger than this one, which produces a wider confidence interval. So at this point, a question that a lot of times students will ask is, why would we settle for anything less than 100% confidence? Wouldn't this be the best possible scenario? If we wanted to be absolutely 100% certain of a correct inference, in other words, of capturing the parameter value inside the confidence interval, the interval has to contain all possible values of the parameter. So we talked about this earlier. Remember, we could construct that interval that goes from 0 to 1. So for the flu example, 100% confidence interval for the population proportion of vaccinated but still developing the flu goes from 0 to 1, which tells us somewhere between 0 and 100% of vaccinated people develop the flu. Obviously, this is not helpful for making any kind of inference. But notice on our problem, just by sacrificing 1% and going down to 99%, we can see that we get a much more narrow interval. In other words, we get a lot of precision gained by accepting that 1% possible error, because our interval is much, much more narrow compared to the 100% confidence interval, which would run anywhere from 0 to 1 or 0 to 100%. So in practice, we settle for less than perfect confidence so we can estimate the parameter value more precisely. It's far more informative to have 99% confidence that the population proportion is between, for example, 0.003 and 0.10 than to have 100% confidence that it is between 0 and 1. In using confidence intervals, we must compromise between desired margin of error and desired confidence of a correct inference. As one improves, the other one gets worse. And so this should say as one improves right here. So here's another example. So this example is going to be 5 bonus points for exam 2. And so what I would like you to do is work parts A, B, and C. For part A, what I would like you to do is go through all of the steps, including the assumptions and the interpretation, just like we did on the previous example. For part B, you don't have to check the assumptions or give the interpretation. You just have to give me the 99% confidence interval. And then I'd like you to answer part C. Alright, so another question that students ask a lot is, well, when am I going to see this in the real world? Why is it important for me to learn about confidence intervals? Pause the video for just a moment and read this poll right here. So you've probably seen articles similar to this one in the past. Notice the article claims majority of Americans back stricter gun laws. Let's apply what we know about confidence intervals. First, notice that the statistic the headline references is 54% support stricter gun laws. Using the notation from the course, we know that their p-hat or their point estimate was 0.4. The article also states that the margin of error is equal to plus or minus 3 percentage points. This informs us that a range of reasonable values for the proportion of all Americans who support gun control can be found by using our formula for a confidence interval. So here we see the actual range is anywhere from 0.51 to 0.57, or 51 to 57% of people support it. Notice this interval lies entirely above 50%. Therefore, the claim made by the headline is reasonable. There are times where this isn't always the case. A lot of news articles will report and base their headline off the point estimate, but then not take into account the margin of error, which really talks about their uncertainty in that value. By having a course like this, you now have a better understanding of why it's important not just to take that point estimate or that statistic we find from a sample, but that we need to account for the uncertainty in that value.